On behalf of Space Education and Research Foundation, and on my personal behalf, I very warmly welcome Professor M.M. Sarin and all the participants of this webinar. This webinar, as you all know, is on atmospheric chemistry and climate change. And this will have 4 lectures. Today is the first lecture, which is on climate forcing by the atmospheric aerosols. And all these talks will be given by Professor Sarin. Before I hand over the mic to Professor Sarin, let me say a few words about him as an introduction. Professor Sarin had a very excellent academic and research career. At present, he is a DST SERB Distinguished Fellow at Physical Research Laboratory and honorary scientist in Geoscience Division of Physical Research Laboratory. He did his MSc Chemistry from Nagpur University and PhD at Physical Research Laboratory, Ahmedabad, which is a unit of Department of Space. He joined PRL and worked at several academic positions, and in 2013 he retired as a senior professor, and since then he has been honorary scientist and the distinguished fellow of this academy that I mentioned. His research interests are atmospheric and aerosol chemistry, chemical oceanography, geochemistry of rivers. He has published 155 research papers in refereed journals. He is fellow. There are 3 science academies in India, and he is fellow of all 3 of them. He has served as project director of ISRO's Geosphere-Biosphere program on atmospheric mineral dust. He is member of International Commission on Atmospheric Chemistry and Global Pollution. He is also a member of Scientific Committee on Oceanic Research. He has served as visiting professor at Woods Hole Oceanographic Institute, Massachusetts in USA, and Ocean Research Institute of Tokyo University in Japan. Currently, he is vice chairman of United Nations group of experts on scientific aspects of marine environmental protection. With these few words, now I request Professor Sarin to deliver his talk, and we all will enjoy listening to him. Professor Sarin, please.
A very good morning to all the listeners from Ahmedabad, India. And I would like to discuss some basic concepts on the climate forcing by atmospheric aerosols. And in the next the 3 talks, I'll further elaborate the concepts on the various constituents of the atmospheric aerosols. So I would like to briefly address this issue that how the climate change has become the most important societal concern in the 21st century. And this is one of the most debatable point in the present day context because of the anthropogenic activities which all of us are responsible for it. And in this context, the atmospheric chemistry plays a very critical role, and that is largely in the climate change. And because of the abundances and the distribution of natural and anthropogenic constituents which are being put into the atmosphere on everyday basis. So, and this influence is largely comes in the form of incoming or is largely due to the incoming or the outgoing solar radiation which gets affected because of the natural and the anthropogenic constituents. And this also has the influence on temperature as well as the precipitation of the clouds. So these are the some of the basic concepts which are most important in the present day context, both for the natural as well as for the anthropogenic constituents. So in the past, there was no much major concern about the anthropogenic constituents, but in the recent years, we have to understand how the role of anthropogenic constituents comes into the atmospheric chemistry, as well as, and then how the climate change is dependent on the atmospheric chemistry. So I would like to address some of these basic issues with you. So the primary question which or the key issue which we had to understand, of course, the climate forcing by anthropogenic aerosol. But what is the role of atmospheric chemistry in amplifying or damping the climate change? Now, the climate change, of course, is a very big is a very broad subject which cannot be addressed in a short time or in a 40-45 minutes of talk. But nevertheless, all of you understand what the climate change means. It is in terms of the long term changes in the weather, as well as in the climate, how the precipitation and how the temperature on the earth's surface is going to change, and the wind systems and the wind regimes and all this are the part of the climate change. So the question which is most important, which we want to address: what are the effects of the aerosols on clouds, their optical properties, and the precipitation and the regional hydrological cycle? So these are all the parts of the climate change which are important, which we have to understand in context of the anthropogenic aerosols, which man is adding to the atmosphere on a everyday basis, on a continuous basis. The climate change is a one of the big issue, because all of us understand the importance of the present day climate change. So in this context, it is then it is also important to understand that the climate also affects the chemical and physical processes that determine the atmospheric composition. Because all of you know that the when the earth has warmed up after the glacial period, we have put more carbon dioxide in the atmosphere. That is because of the ocean. Of course, man is putting more carbon dioxide in the atmosphere after the or since the industrial revolution. But when the earth warmed up and when we came through the glacial age, we had put more carbon dioxide into the atmosphere. That is because of the warming of the ocean. So I'll deal with that aspect in a separate talk. But it is very important that the chemistry is responsible for the climate change, and climate change also is responsible for the chemical and physical processes that determine the atmospheric composition. So this is what the simple understanding which we have to keep in mind, and this is largely happens through the changes in the temperature and water vapor and the incoming shortwave radiation. So these are the main factors which are responsible for the climate affecting the physical processes as well as the atmospheric composition. So in this context, it is also now relevant that the interactions between the climate, physical and chemical process are very intricate, because we have to understand all the three systems together. Climate we have to understand the physical the processes, we have to understand the chemical process, and these are of course very intricate, and basically they are intricate because of the non-linear behavior of these processes. They involve the feedbacks, which I'll discuss in this talk. And so we need to understand the climate, physics, chemistry system in a holistic way. Then only we can try to understand how the aerosols and the atmospheric chemistry are going to have the influence on the climate change. So one of the very simple examples of this the chemistry or the effect of chemistry on the climate is the influence of anthropogenic aerosol, as important as the greenhouse gases. So I'll not go into much of the greenhouse gases, because greenhouses the warming potential has been uh, well understood in the recent years. But the warming or the cooling effect by the aerosol is something which is more debatable, and that's where the present day efforts are going on to understand how the anthropogenic aerosols are going to cool or warm the atmosphere. So, but this is as important as the greenhouse gases, because greenhouse gases are being much understood that they are causing the global warming. So this we know in this aspect. So let us see the anthropogenic aerosols. Now, what are these anthropogenic aerosols? These are primarily in the submicron to micrometer size range, and they are composed of numerous inorganic as well as the organic species, and they can be broadly classified into three categories. One is the sulfates, which are coming from both natural and the anthropogenic sources, mainly now from the anthropogenic sources, because sulfates are being added from all the industries and various other commercial the agencies. And then we have this carbonaceous aerosols, which I will deal separately in a talk tomorrow. And these consist of primarily the black carbon, which we refer as BC, and then the organic carbon, which is referred as the OC in the subsequent talk. And then the most important is the dust, which is third constituent of the atmosphere. Dust is a perennial constituent in the atmosphere, so we have to understand the role of dust also in the climate as well as in the chemistry scenario. So dust is a very potential constituent, and I'll deal with this dust also in a separate talk day after tomorrow. So what one has to keep in mind that the anthropogenic aerosols which we are talking about are primarily the sulfates, which are coming from anthropogenic sources. Some of them are from natural. Carbonaceous are largely coming from the biomass burning, fossil fuel, as well as the coal burning. And dust, as I said, is a perennial constituent and present in the atmosphere, and also being added by the various other anthropogenic activities. But natural dust sources are very important. So these constituents have increased the global mean aerosol burden from pre-industrial time to the present day. This is very important. So one has to keep this in mind that in the last 200 years, the concentration of sulfates, carbonaceous aerosol dust in the atmosphere has increased substantially, and that is the reason for the cause and the debate or the concern that how the atmosphere chemistry is going to change in the context of these type of anthropogenic aerosol, and what are the influence this is going to have. So let us try to understand further what are the simple aerosol components which we are talking about. As I said in the previous slide, so there are two types which I will dwell upon. One is the natural, and these are the units in teragrams per year. This is the global burden as of today. So you can see that in the natural are of the order of 3100, and the anthropogenic are about 450. And in the natural context, we are basically talking about the mineral dust, sea salts, which come from the marine, because oceans cover the large surface of the earth. So we have the sea salts, and the others contribute to some small level. So these are the constituents which are important in our context of the natural aerosol, which have been there from the time immemorial. That the natural our aerosols are part of the atmosphere, and they are part of the atmospheric chemistry, and they are part of the climate change. Now, once we get into the anthropogenic aerosols, so these are having a burden of about 450 as of today, or close to 500 compared to your natural aerosols. So they are still about uh, uh, not as high as the natural, but nevertheless, it is important to see that they are significant in the atmosphere. So the sulfates are basically coming from the gas phase oxidation of sulfur dioxide by the OH radical. OH is very important in the atmosphere, because whatever we put in the atmosphere as a sort of pollutant, that gets oxidized by the OH. So and sulfur dioxide is one of the anthropogenic constituents, comes from the man-made activities. Of course, there are natural sources also, like volcanoes and those. But we are right now in this context, we are trying to address on the gas phase oxidation of sulfur dioxide, which is coming from the anthropogenic sources, and that is gets oxidized by the OH radical, because OH is the most oxidizing agent in the atmosphere. So that is one aspect. Then we have the biomass burning products, which I told you in the previous slide about the black carbon and the organic carbon, and they are also adding substantial amount of aerosol constituents in the atmosphere. Next comes the nitrate, and then we have the other organics which are also important. So these all put together, we have the aerosol components which are present in the atmosphere. So this is what we have to understand, and we have to see that the what how we understand the impact of these both natural as well as the anthropogenic aerosols in the climate change scenario. But having said that, I made a very clear statement that the global warming by the anthropogenic greenhouse gases is well understood. So I will not go into those details in this particular talk. Then what happens to these both natural as well as the anthropogenic aerosols? So further enhancements are expected. This is something which is very important, and that is for the dust because of the changes in the soil moisture. That again depends on the precipitation rainfall. So if soil moisture decreases, then you will have more suspension of dust in the atmosphere, as well as the land use and the other the wind fields which are going to change. So and you have the long range transport of dust from the desert regions as well as from the other anthropogenic land use cover change. So these are all going to have the further enhancement of these of the dust. Sulfates are, as I said, are coming from the anthropogenic sources, industries, and then. But there is a very important and perennial source of sulfate comes from the oceanic biomass, and that is because ocean has the primary productivity. And if primary productivity increases in the ocean, which the efforts have been tried, I will discuss on these aspects in my fourth talk. If dust is being added from the atmosphere, that means basically iron is being added from the atmosphere. So iron acts as a micronutrient for the enhancing the biological productivity in the ocean, and the biological productivity enhances, then you will produce more of dimethyl sulfide, which is a gas, which is and that gets finally oxidized to sulfate, and that sulfate acts as a cloud condensation nuclei. I will address this particular aspect of CCN, how these are. So there are not only the sources of sulfate coming from the industries, but it is also important to see that how the oceans will also can enhance the sulfate contribution in the atmosphere through this kind of biological changes in the ocean as a consequence of the climate change, or vice versa. If the oceans are having, so that will have impact on the climate change, or the climate change is there, then the oceans will behave in a different way. So it's a feedback as well as as well as the interactive system. And then, of course, the last aspect is the black carbon and the organic carbon, which is coming from the fossil fuel as well as biomass burning and coal burning. Coal burning is more of regional sources, so and it is significant, but it is not significant for organic carbon, but it is certainly significant for the black carbon. But the fossil fuel is a major concern on the worldwide use of diesel, petrol. So most of the black carbon, organic carbon is coming, and the forest fires, biomass burning, agriculture waste, residue. These are all adding to the black carbon and organic carbon in the atmosphere. So which I will deal separately on the carbonaceous aerosol in the tomorrow's talk. So let us go back to the primary understanding that how does the radiative forcing, that means radiative forcing means the radiation which is coming from the sun, how much is retained by the earth, and how much is emitted back, or how much is reflected back into the atmosphere. So we are able to maintain the balance of the heat which is comes from the sun and how much is going out. So this is where the simple understanding of the greenhouse gases is there, that they are distributed uniformly over the globe. This is something which is very important. That's why the global warming by the greenhouse gases is becoming important, or it has become important in the recent years, and people have understood this, that what are the differences in the northern hemisphere versus southern hemisphere. So that those are the issues which are important, but we'll not get into too much detail because the greenhouse gases and the radiative forcing from greenhouse gases is well understood in the present day context. So this is and primarily because they absorb the IR radiation, long wave radiation, and they reflect the the outgoing the radiation, long wave radiation, and then also uh, they have the radiation of the radiation at the top of the atmosphere. So this is something which is very important, that how the greenhouse gases are maintaining the heat budget in the earth. So in terms of the of radiative forcing, which is changes in the long wave radiation, incoming and outgoing radiation. So since the early 20th century, which we have now have been understanding for a long time, there is a net heating of the order of 2.4 watt meter square. That means the whatever heat which is coming from the sun and what is escaping out, there is a, a difference of 2.4 or 2.5 watt meter square. That means we are retaining that much heat in the Earth's atmosphere, and this is what is important, or is known as the global warming, which is important in the present day context of climate change as well as the global warming, and which are integrated. So most of this it comes from the carbon dioxide. All of you have understood that the how carbon dioxide is being increasing in the atmosphere from the industrial time, and how. So this is the one of the most significant greenhouse gas which is adding into the atmosphere, and we are having the maximum the warming is due to the carbon dioxide. Then comes the methane, and then we have the N2O and the other halocarbons. These are all added together. If you see these numbers, they all add up to 2.4 watt meter square. So this is a well understood concept, that the greenhouse gases are heating up the atmosphere. So I will not go into too much details about these things, because this is not the primary focus of our today's understanding. So what is important now is the aerosols. Now, compared to the gases, or compared to the well mixed greenhouse gases, aerosols have the short lifetime. It is of the order of week or even less. That means 3 to 4 days, because they are removed from the atmosphere very fast. But they increase the reflection of solar radiation through a variety of reasons. And this is sorry for the interruption. We'll continue on this. So these the aerosols understanding is something which is very important. How it is going to interact with the solar radiation, and something which we must see that how these are responsible for the radiative forcing on the top of the atmosphere. So the changes in the absorbed solar radiation, and if you see the global range is of the order of minus 0.5 to minus 2.5 watt per meter square. Now this is something which is very important. This is the present day understanding. So that means in contrast to the greenhouse gases, we are having the net cooling effect due to the aerosol. This is a very simple minded approach, which we have to further understand that how these aerosols are having a cooling effect compared to the warming potential of the greenhouse gases. So. So climate change in the context of anthropogenic aerosols. So forcing it to the climate change is coming from the changes in the aerosol concentration and the properties. This is something which is very important. So if the forcing is primarily because of the concentration and the properties of the aerosol, so and the effect is seen in the two ways. So this is something which I will try to explain in this, and that is the purpose of this particular understanding, that how are the direct effects of aerosols are important, and how are the indirect effects of the aerosols are important as a cloud condensation nuclei, which you see here, and also the absorption and scattering of the solar radiation, which is considered as the direct effect. So I will try to explain this basic concept in this particular context of the climate change, and largely due to the anthropogenic aerosol. So as I said, the lifetime of the aerosols is very small. So this we have to keep in the mind. So, and the response of this the climate change, how do we see that the climate change, how the response is there? So this will be change in the surface temperature, and then precipitation pattern and the intensity of the precipitation. This is are the response which you can see whether the climate is changing, because it's a very important that how do we know what is the climate change? Climate change is nothing. It has to be seen in terms of the response. So response has to be seen whether there are going to be changes in surface temperature and the precipitation, rainfall, and the intensity. So this is so with the simple understanding. Uh, due to aerosols is primarily determined largely by the parameters called omega. Uh, this implies that the single window which we use in the atmospheric chemistry, and that is the ability to absorb the solar something important, and the direct impact of the aerosol. So omega is nothing but the ratio of the scattering efficiency of the aerosol and some of the absorbing efficiency and the scattering efficiency. So this is a simple parameter which we call as the single scattering albedo, and that determines how the aerosols are directly interacting with the atmosphere. So scattering aerosols, the one example which I have given has the major impact of the climate or the atmosphere as a negative the forcing. That means it is cooling the atmosphere, and the omega for sulfate is very close to 1. So when the both scattering and the sum of the absorbing and scattering efficiency is equal to 1, so that means the that particular constituent of the atmosphere is having a negative forcing. That means and we all know that sulfate of the cooling or is the constituent which has the cooling effect in the atmosphere. That's why people are trying to do some engineering aspect that we should add more sulfate in the atmosphere. But that's a different aspect. I will not get to much. The absorbing aerosol, and one of the most common examples is the carbon, which is the most important constituent in the atmosphere, and we have been debating on this on gas. So people understand the direct forcing from the sol comes, but most of the single scattering albedo in the hemisphere is very close to 0.95 range. So that means the 0.85, 0.9. So that means the most of the aerosols in the northern hemisphere are close to omega value of 1. So that means we will have a
साउंड नहीं आ रही आपकी, इसमें कुछ गड़बड़ हो गया शायद। आप ये उठा दीजिए उसको, ये ले लीजिए।
So let us try to understand the indirect radiative forcing of aerosol, or the what we also refer as the cloud condensation nuclei. So I have tried to explain this in a simple concept, that if you have we have a cloud which is very clean and which is not impregnated with the aerosol, which you see on the right hand side. So there is a simple understanding that these have the high precipitation efficiency. They have the large droplets, because large droplets are very easy to condense together. So, and you can see the precipitation efficiency compared to the dirty clouds, or the clouds which are impregnated with the aerosols as finally decreased. So this is mainly because of the increase in the droplet number, because once you add the anthropogenic aerosols, or the aerosol constituents into the cloud, it enhances the number density of the clouds, which you can see the comparison in a conceptual way. So there is an increase in the droplet number, and there is a decrease in the droplet radius. So that means you produce very fine drops, and you increase the numbers. So number density increases, but the drop size or drop the radius decreases compared to this and compared. So this is a simple understanding, and because of this, there is a decrease in the precipitation efficiency of the clouds, because you are producing very fine droplets which are not easy to condense. That's why the cloud efficiency decreases, and this also has an increase in the cloud lifetime. So lifetime of the cloud will be much longer compared to this particular clean clouds, which has a very high precipitation efficiency, as well as the larger. So this is a very natural scenario which we understand in the simple system. But this is what is we are trying to understand: what happens when the anthropogenic aerosols are being added to the cloud system. So you are going to decrease the precipitation efficiency by simple understanding of the increase in the droplet number, and the radius, the droplet radius. So this will have the finally impact on the cloud, the albedo, because you are now making a very fine cloud. So this will have the enhanced cooling. So this is the simple way to understand the indirect forcing due to the aerosols. And this is something which is important, that how the some of the constituents or the aerosol constituents are acting as a cloud condensation nuclei. So CCM stands for the cloud condensation nuclei, and this is considered as the indirect effect. This is a very simple understanding, conceptual understanding, which is important. Okay, so now there have been some experiments. There has been some way to understand whether this is really true or not. So there has been some studies based on the polluted clouds, where the if the aerosol number concentration below the cloud base it exceeds the 300 per centimeter cube. So there has been a very far less decrease in the drizzle size drops that compared to the clean cloud. So people have observed this kind of issue, which I tried to explain in the previous one, that the droplet size decreases, and the density or number density of the drops increases. So this has been observed in some of the observations, and the people have tried to show that there is a evidence for the cloud lifetime effect. So depending on the number of aerosols below the cloud base. So the understanding of the basic concept is being understood in based on the observations also. Okay, so now the other aspect is that the climate system always has a feedback, because we cannot have a one-way interaction, because there is always feedback. So now I try to so far address that we have the global warming due to the greenhouse gases, and we have a general understanding that the aerosols are doing the cooling effect in the atmosphere. This can be regional, and this can be slightly on a larger spatial scale, but this cannot be considered as the global phenomena. But nevertheless, the understanding is there that the aerosols are having a cooling effect, and the greenhouse gases are having the warming effect. So this is a simple understanding so far I have tried to convey to all of you. So now, but among the aerosols also there is a cloud feedback understanding, that the how the some of the aerosols can act as a also the heating effect, which is contrary to what I tried to explain, that the direct effect of aerosols and the indirect effect of aerosol. So now if you take the soot particles or the black carbon, and they are considered as the ice nuclei, because in the supercooled clouds at -5 to -20 degrees centigrades in the high latitude regions. So if we have the soot particles which are interacting with the cloud from the biomass burning and fossil fuel emissions, so after some time there is oxidation of these constituents, and because of the oxidation, the surface chemical groups which are there in soot particles, because soot particles is a very composite particle, contains the hydrocarbons and contains the other important chemical constituents. So these surface chemical groups which are there in the soot particle, these form the hydrogen bond with the water molecules, because cloud is nothing but the water contains. So all the hydrogen bonding occurs because of the water molecules which are present. Now, if these soot particles are interacting with the water molecules with the hydrogen bond, so what is going to have that in the ice? You know, in the high supersaturated environment, we are going to have the decrease in the liquid water parts. This is something which is very important. That means you are taking away the water from the clouds. So that will decrease the liquid water part, which is very important, because in general the short wave radiation penetrates through the liquid, which has the attenuation effect. But if you decrease the liquid water lot, so the more shortwave radiation will reach the earth. This is a simple understanding in this. So if we are removing the water, we are allowing more short wave the solar radiation to reach the Earth's surface. So this will have a more heating effect on the atmosphere. So more heating due to this. So this is going to have a counter the cooling effect which we have talked about in the last few minutes of the aerosol. So there is a feedback now because of the some of the particles. So instead of now cooling the atmosphere due to anthropogenic aerosol, we are invoking the concept of heating the atmosphere because of the interaction with the clouds and because of the soot particles which are being added into the atmosphere. So this is another type of understanding which we have to keep in mind, that the how the feedback mechanisms are also important in the present day context and in the atmosphere. So there has been some simulation studies which has been done based on the previous concept which I talked about. People have seen that that if you take the liquid water path, which I talked about in the previous slides, that if there is no BC, and with the 1% of BC concentration put in the system, and if you have 10% BC concentration in system, and what happens to the liquid water path? So you can see that the liquid water path increases when there is no black carbon, which I explained in this concept, because uh, in this concept, that the hydrogen bonding with the soot particles will take away all the water molecules, so liquid water path will decrease. So this concept is being studied based on the modeling approach, that if there is no black carbon, then the liquid water path is more, and if there is 1% BC, then you have a liquid water path decreases, and if you have 10% BC, there is a further decrease in the liquid water path. So this is in units of grams per meter square. This is a standard way of doing the simulation, and most of these are important are there in the northern hemisphere, because that's where we have more anthropogenic activities compared to the southern hemisphere. Now, in response to this liquid water path, which you have seen in this top picture, what happens to the short wave radiation now? If you see that when there was 10% BC, you have more penetration of the short wave radiation. So this is something which is what the previous cartoon or the conceptual way of understanding was there, that you have more penetration of the short wave radiation when there is a high concentration of BC in the atmosphere, and when you have the 1% BC, the short wave penetration is less, and when you have no BC, there's no penetration of the short wave radiation. That means you have a negative forcing, but in this case you have the positive effect. You are allowing more short wave radiation to come to the Earth. So this is a very important way to understand how does the feedback mechanism as well as the indirect effect of the aerosols is important. So, so coming further to the now final understanding, because whatever I said in the last couple of minutes, that the radiative forcing due to the aerosols. So the important thing is, what are the uncertainties which are surrounding the current understanding of the radiative forcing due to aerosol? The size of this arrow, or the thickness of this arrow, tells you the greater the thickness, higher is the uncertainty because of that particular concept. So let us see the first one. The smallest uncertainty is coming from the distribution and the concentration. That means we have to still understand what is the distribution and the concentration of the atmospheric aerosol. But most of the uncertainty which is coming in our understanding and coming in the way of putting the impact of the aerosols on the climate change is largely because of the size and the optical properties of the aerosol, because this is something which is very important, and that depends on the chemical composition as well as and which is more difficult to measure. Then we also have to understand, or the uncertainties coming into the picture, because in the radiative forcing due to aerosol is largely coming from the aerosols which are natural or anthropogenic, and this is a very important aspect, how the sulfates are the secondary constituents in the atmosphere, and what are the role of the secondary particles in the atmosphere. This is a very important aspect. So the uncertainty in our understanding is also due to the sources of natural as well as the anthropogenic error. Another major uncertainty, because thickness of this arrow is pointing towards the chemical composition of aerosol. Now people are trying to understand the chemical composition of aerosol, and unlike the greenhouse gases, which are well mixed in the atmosphere, interhemispheric differences are not large, but aerosols are very highly regional, highly localized. So one has to understand the chemical composition of aerosol both on a regional as well as on a spatial scale. So this is a important bottleneck in our understanding of the radiative forcing due to aerosols. Okay, so let us now try to understand the whatever, or I will try to summarize whatever I have said in the last 20 to 30 minutes. That the aerosol radiative forcing due to the due to both natural and anthropogenic aerosols. This is what this picture is trying to convey. I'll try to explain this. And the values have been averaged over the ocean with respect to the longitude. Of course, you see a latitude distribution of the forcing, which is in units of watt per meter square. But this is very important to see that the how this forcing is there in the atmosphere, top of the atmosphere, and at the surface. So this is the message which is coming from this is that the surface have been averaged over the mean with respect to the longitude. So that means this is the over the oceans. This is a mean has been taken, whereas the atmosphere and the top of the atmosphere. So what you see a very conspicuous trend. There is a south-north gradient. So if you go from southern hemisphere to northern hemisphere, you see a south-north gradient. That means almost of the order of minus 25 watt per meter square in the solar radiation. Uh, so this is something which is known as the heating of the atmosphere. So and the forcing which is important. And then you also see a negative gradient in the ocean solar heating. That means this is the surface heating. So you see a negative trend in this. So this is what we have been trying to talk about, that the aerosols has been having a counter impact compared to the greenhouse gases. That the aerosols are having the cooling effect. But if you see the top of the atmosphere, there is a net cooling of the order of whatever which I explained in the previous slides, of the order of 5 watt per meter square. But on the atmosphere as such is heating, but the surface is cooling, as well as the top of the atmosphere is cooling. So this is the simple understanding which we have so far about the aerosol, but this is a very elementary and simple understanding so far about the anthropogenic aerosols. So these are based on simulations as well as the observations. So in coming to the some of the observations, this is the Indo-Asian haze transported thousands of kilometers to the equatorial Indian Ocean. This was mainly was part of the atmospheric the brown cloud program, which was there in the Indian Ocean experiment, and its impact on the radiate forcing and the regional and the global climate, how the response is there, how it is there, and then also to understand the ENSO phenomena, which is nothing but the El Nino Southern Oscillation, which I will not get into too much details right now. So these are was the basic objective of the atmospheric brown cloud, to understand that how the processes over the ocean or in the marine atmospheric boundary layer are important, and also how the temperature variability is can be understood in that. So coming to the future, how do we are going to understand our approach in the future scenario? Aerosol radiative forcing. How do we reduce the uncertainty, which I tried to explain in the previous slide also, that the how do we try it. So we need a full range of observations, and these observations have to be chemical, physical, and optical properties of the aerosol. So we must understand the size, composition, and the optical properties of the aerosol, and the long-term continuous measurements and the seasonal variation, which is very important. The estimates which have to be done, because unless we know the long-term continuous measurement, because the lifetime of aerosols is very small, as well as there are regional variation. So we have to have the critical parameterization of the hygroscopic properties of the uh, of the mixed aerosols, because aerosols in the atmosphere are not are individual constituents. The dust is mixed with the black carbon, and all the sea salts are mixed with the dust, and so we have a very mixed type of aerosols in the atmosphere. So we have to understand uh, the uh, the absorption properties of mixed aerosol, and these mainly the black carbon, organic carbon, and the dust. I will in the next 2 or 3 talks, I will dwell upon the role of black carbon, organic carbon in the atmosphere. So this was the understanding to see as a basic on the anthropogenic aerosols, which are important in the atmospheric radiative forcing. So formation of secondary organic aerosol, this is a big question mark. We do not have much understanding so far, but this is the most important thing, because secondary aerosols, organic aerosols, are very important in the atmosphere. So this understanding has to be there in our future approach. Okay, so there is a some concept which has so far evolved, that to understanding that the and this is one of the climate impact, or the climate forcing from the anthropogenic aerosol. The question which people ask is that, can anthropogenic aerosol emissions in the northern hemisphere influence the precipitation in the tropics? So I would like you to focus on this region, because we are talking about the tropics. So you can see there is this is the observed phenomena, which is shown by the black dots, and this is the global circulation model, which is also trying to mimic, except that there is some differences in the observation and the model in the tropical area. But what this the particular study, or what this particular the message which is trying to get out from this comparison from long-term observations and the data versus the model, it says that the striking feature in the is important for the in the model and the observation, and there is a southward shift in the precipitation. So if you see that the precipitation is increasing in the now in the southern in the south of equator, which is what it is. You can see that this is a decrease in the precipitation, but when you come to the south of the tropical region, there is an increase in the precipitation. So there's a decrease in the equator from 20 degree north to equator. So there's a decrease from the 20 degree north to equator, and there's an increase in the equator to the 20 degree south. So this is a something which is very important, that people are trying to understand this the aspect, and this has a very major implications, that the does anthropogenic aerosols in the atmosphere are going to influence the precipitation in the tropics. This is something which is we have to understand, and there has to be more understanding in our uh, 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 have to be developed in the due course of time. So I will try to come to the conclusion. So the global hydrological cycle, which has been now looked at it. So there are some understanding in this aspect. So people are trying to say that the hydrological or hydrologic cycle will be weaker in the period from 2030 to 2050 compared to the present day climate. This is very important conclusion, which has come from the study which was done several years ago. That the and on the global hydrologic cycle, and this has both the direct and the indirect effects of the aerosol, which I tried to discuss in the last 1 hour. and the precipitation would decrease by 0.4% per degree centigrade. That means decrease in the temperature. It will have net cooling on the system, and then the only greenhouse gases are going to have the increased precipitation by 0.7% per degree centigrade. So what the message which is this study is trying to give is that the greenhouses gases are going to have certainly the increase in the or warming potential in the atmosphere. They are going to increase the precipitation. So if we do not have the anthropogenic aerosol, we'll have the increase in the precipitation by 0.7% per degree. This is what people have been talking about, that in the global warming scenario, you will have more of precipitation. But if we have the precipitation can decrease because of the impact from the aerosol. So you will have a decrease in the precipitation, and which is largely because of the decrease in the temperature and coming from the aerosols. So this is something which is important in the climate change. So, finally, I would conclude that there is a need for very carefully evaluated coupled aerosol chemistry models. So, which is what? So, not only we need the models, but we need the chemistry built into these models, and that is something which is important in the scenario to understand the cooling effect due to aerosol and the warming potential from the greenhouse gases. So there is a big debate in the atmospheric community, that how do we understand the direct and the indirect effect of the aerosol on the climate, or on the atmospheric chemistry, and atmospheric chemistry is going to have the influence on the climate. So thank you very much for your attention, and I would take any questions if they are you would like to address me for more on that. So thank you. No, I can't. Kindly. Thank you, sir. Next. Uh, uh,
इससे नहीं जाता है
hmm?
नहीं अच्छा ठीक है आपको कमेंट वगैरह ही होंगे तो दैट यू विल नॉट नो कर सकते हैं